Okay, so this is roughly the 6th time I tried to make this video over the last couple months. A lot of little details to work out, but okay, so this is making a quad, and I thought of doing a triangle, but a quad is going to be more useful, and as you'll see in this video, I do this EBO element buffer object, which is not the simplest way to make a triangle or quad, but this is the way I want to do it for these tutorials. And so I realized this is all in the tutorials folder in the code. Let me just clear this out. So there's a collections directory in the code, or sorry, on the GitHub basically. And later I'm going to be putting things that are interesting, that maybe they weren't directly part of the tutorials, but for example, just making a triangle, let's say without the EBO. There's also other things that you can draw. Let's see where the draw function is occurring. I'm going to roughly go through and explain all the code in a second, but here we draw triangles. There are other primitives that you can draw, like triangle strips, lines and points and so on. So that kind of thing might end up in the collections. I'll probably make videos about them, stuff like that. Okay, so let me show you what this does right now. I use kind of the Unix style commands here, as you see. So I do like this, even though it will reverse it like that for the Windows style. And then if I just run this, it will tell me I need an argument. We'll do main.c, compiles, and here we go. This is it for now. Okay, and there's also a full screen option. I'll just demonstrate that. I'm not 100% sure it's going to come up in the video here, but I think it will. If I change that to 1 and do that, there it is. I hope you can see that. Now to quit, personally I do the Windows key, and then it's still running, so you want to click here and close. Okay, a little awkward. Later it'd be nice to have a better way of closing the application. Also, it is using probably a full CPU core, 100%, because we're not sleeping in the loop here. But that'll have to be another video. And like I said, I may do a video at some point with a triangle that will be simpler. But, you know, this is what I did, so rather than having one video about the triangle and then kind of changing it to a quad, I just went straight for the quad. Now I'm not even sure that I use this parameter here. Maybe I do. Yeah, it's used. Okay, so we have this if-def macro. I think that's a macro. Anyway, it's a pre-compiler command, I guess. So anyway, it checks if it's Windows or Cygwin. And I believe if you're using Cygwin, it won't have this there. Not sure. But anyway, so we include these GLAD headers. And the GLAD headers are for Windows for telling OpenGL, or GLFW in this case, where your, I believe it's where your functions are, for your OpenGL functions. So it's something we need for Windows, but not for the other platforms, Linux and Mac, which, by the way, I just tested, are working as well. They have their own little run scripts. And yeah, I talked about those in previous videos. So in the libraries, I added the GLAD library, and I can't remember if I made a video on that yet. If I didn't, I will make one. It's not that complicated. You download it from the website. But yeah, so look for a separate video on that if you just need help downloading the library. Now I put it in the project. Normally people would put it system-wide, but I just kind of wanted this to to make it easier, if possible, for people just to download from GitHub and maybe it will work out of the box. So that's why I included it in the project. I don't believe it's that big in terms of size. Okay, so yeah, so let's get into the code. So this is the Windows only stuff here. We're including GLFW, and by the way, as you notice, main.c, same for the 3 platforms, but we do have some specific stuff for Windows here. Let me get rid of this. Okay, we include standard input-output for the C programming language. So we have print and all that stuff. Screen width and screen height. I forget why I put it in these weird terms. Maybe I'll figure that out. This is just something I have from the past. We create this video mode, and there's going to be some GLFW stuff in here. I'm not sure. I don't know everything about GLFW, but we'll see when this gets used. And it has a window. So it has a window and it has a mode. I'm going to switch this back to 0. That will get rid of the full screen stuff going on. We'll see that later. Then we have some little functions here. Set up vertex array, because I just kind of took out what is kind of boilerplate stuff, and I'll be doing more of that in the future. But build shaders is a function that builds a shader, and it's pretty good little function there. And set up vertex array, it does what it says on the tin. So we will get into that. Those 2 functions are kind of boilerplate stuff. You don't actually need to know really what's going on in those functions, but we will go through them. And then we have this thing called a vertex array object, which I will explain more. So when we use it. But so then we have our shader source, the vertex shader, and the fragment shader. Now, I recommended before, if you want more reading on this, I believe it's learnopengl.com. No affiliation here, but that's kind of the best source. If you want an explanation, I will briefly. This is the code, and I'll tell you why it looks weird. But this is the code that determines where the vertices appear on the screen. And so the rendering pipeline has one step. A critical step is rasterization. Rasterization is where you have a triangle and you determine which pixels to render based on that triangle. It's basically drawing a triangle on a screen, but to be more specific, a screen is a frame buffer, and so it's just whatever your dimensions are of the window or screen that you're rendering to. And so let's say it's these dimensions, what is that? I don't know, but you have like a width and a height, right? So multiply that to get the number of pixels, and each pixel needs red, green, blue, and possibly alpha for the opacity. But this doesn't handle color or anything like that. This just determines where the vertices appear for a triangle. So if you had, for example, a triangle that is rotating in 3D space, you would want to put that rotation stuff in the vertex shader. You can also, so if you put in the vertex shader, I believe it will get calculated per vertex on the GPU. But if you calculated it somewhere else, like in your while loop, that will get calculated on the CPU, and then you can pass it to your shader with what's called a uniform. And we'll get into uniforms later, but okay, so this is a normal thing that you do. So you might do the rotation here. It will happen per per vertex. So this code gets run per vertex. Okay, so the fragment shader, so all we're doing in OpenGL, essentially, there's a little bit more to it, but mainly what we're doing is we're drawing triangles. So all the 3D stuff is really kind of a magic show where we're actually just drawing triangles. If you rotate a triangle in 3D space and then you flatten it onto a two-dimensional screen, the result will also be a triangle. So, all right, so let's talk about the fragment shader. So once you have that triangle after the rasterization process, then every pixel that renders something for that triangle, every pixel the color output will be determined by the fragment shader. So these get linked as one shader program, but the fragment shader determines basically the color that gets outputted and the opacity, potentially. So RGBA. Some cases just RGB. And so this runs per pixel, basically. We call them fragments, though, not pixels. Pixel is like a specific part of your screen, your display, but the fragment is I think more abstract, but it's basically talking about a pixel. And okay, so all kinds of things can be done here in the fragment shader. And so just remember that this code for the vertex shader runs per vertex, and this fragment shader code runs per fragment. It runs once for every fragment. So that's where the GPU is powerful, because it uses the shader program and it runs it many times, basically the same program with different inputs based on some coordinates. So, all right, so why does this look so weird? Okay, later we're going to be separating our fragment shaders and vertex shaders into separate files. And in Sublime Text, I don't know if I have it here yet. There is a plugin that has GLSL syntax highlighting that I will be installing and using later. But right now, we don't have the separate file yet, so we can just do it here. And this is important, that your version is not do not put space. It's sort of a quirk, but it needs to be the first line, okay? So that's why it's here, and I didn't, write like this, which would have been easier to read, something like this, whatever. But anyway, no, put it here. And 330 is a version that has a lot of compatibility. The first three is the major, and second is minor, so it's version 3.3. The layout, so location equals 0. We'll get into this later, but this is where the vertex data is being passed in. Okay, and the in is for input, so we need a in for our vertex shader. Vec3 is a what do you call it? A 3x1 or a 1x3? I forget, but it's like this: X, Y, Z. Okay. And I think it's a 3x1 vertex, or sorry, well, I'm thinking in matrices. If it were a matrix, it would be a 3x1, but it's just a vec3. It's a vector with 3 components, x, y, z. Okay, so that's the input, and we call that a pos. Not the best name, but okay, a pos, and so these shaders, as you'll notice, they have main functions. So that's where the code starts. And GL position. So this is a, what is that called? A global, or a built-in variable, I believe. And so this gives us it outputs the position that is going to be used in the rasterization process. So it's a vec4. Now I believe this is opacity. No, this is the vertex shader. I forget why we have the 1.0, because sometimes you have a 1.0 for working with augmented matrices. Basically, if you're rotating in three-dimensional space, you use 4x4 matrices. I just kind of forget what, if it's opacity or if it's for working with augmented matrices. But here we go. So that's the position. It's simply a pass-through. It's simply being passed through, and we'll get to later in the code where I'm actually writing the vertex data by hand. Now onto the vertex fragment shader. It has an output, which is a vec4, so that's RGBA, and we're using floats here. So this is 100% red, RGB, right? This is 50% green and 20% blue, and the opacity is set for total opacity, no transparency. So the triangle gets determined in here, and the color of each fragment within the triangle gets determined here in the fragment shader. Okay, now for our main function. So we initialize, I'm going to start going a little faster through these parts, but we initialize GLFW. We give it some window hints. I believe this is from the GLFW website, so I don't exactly remember what this is about, these two lines, but this is our version 3.3 that we're using. I have if full screen, and so for full screen we need a mode. This is just from the GLFW website on how to do full screen. They have good documentation there if you want more information. I tried to find out why this needs to be done, but I could not really find out why. Anyway, it's what it says to do on the GLFW website, so that's what I'm doing, and it works. I forget if this is on the website or if I added it for some reason, but there it is. And the window equals create window. Yeah, I think this is just the GLFW stuff from the website. So how to create full screen. If it's not full screen, we pass in the screen width and screen height. You can change these numbers, obviously, to what you want. I think I did this 8x5. I don't know why. Oh, you know what? I was working on the Mac. Mac is 16:10 aspect ratio, MacBooks and so on. So that's why it's 8x5. I was working on an Apple computer. So I did like that. So I made it that, yeah, anyway, it doesn't matter. Okay, and yeah, so the window gets created, and then we check if it's not there. We say failed to create and terminate. We make the context current. That is basically just saying, hey, we're going to use this window that we made. You can actually have multiple contexts if that's for some reason something you need. For our purposes, I think we don't need more than one. And so then here's loading in, oh, whoops. Okay, here's loading in GLAD, loading in the headers for Windows-specific OpenGL stuff. And so we do that. If we're not using Windows, we ignore this stuff. And okay, so now we have a shader program, and this is how we do int. So you'll see this a lot in OpenGL, and actually I think, technically it's just maybe supposed to be GL uint, rather like this, which is an OpenGL unsigned int. But this just gets mapped to unsigned int, I believe. But it doesn't matter. I just use an int. And so these ints, or GL uints, etc., are often used as handles. They're just little identifiers for things like programs and other stuff, OpenGL. So this is a common, I don't know if you call it a workflow, but pattern. It's a common pattern. So yeah, so that's what we're doing here. So we have the create program function. So let's take a look at that right now. So, oh, sorry. we're going to look at build shaders. GL create program is a built-in OpenGL function, and it creates the program for the shader. And then, so I build the shader, and I pass in shader program. So let's take a look at build shaders down here. Oh, you know what? Actually, I'm going to leave these two functions for the end because some people might not care that much. You just need to know what they do. You don't really need to know the nuts and bolts of it, but at the end I will go over them, so for those who want to know. But yeah, it's building a shader program. And also, it's hard-coded at this point, I believe. The fragment shader, let me see here. Vertex shader, where is this coming from? Vertex shader source, okay, Vertex shader source, yeah. This is sort of all hard-coded, and later I'm going to make it so that it gets passed in, which is better, because we're going to have multiple shader programs. Okay, so where were we? Here, vertex array, so I'm going to do that at the end. We bind the vertex array. Think of it like this: you can have a vertex array. For example, if you're making a 2D game, you would probably have, let's say you have a vertex array object that is just a rectangle. And just with a rectangle, you can pass in all kinds of textures to make your sprites and everything. And so maybe you have one that's sort of a static. Sorry, when it comes to your shader programs, you'll have maybe a static one that doesn't change. Then you might have one that you use for walk animations and so on. But if all of those different shaders that you're using, just use a set of vertices that it looks like a rectangle, then you can use the same vertex array object for all of them. And even though there are maybe different sizes, you would pass in data in the form of what we call uniforms, and that could be used to scale the rectangle, scale and transpose the rectangle to the correct position. That can be done in the vertex shader. So you could use a vertex array object for all of that. Okay, so anyway, so we bind it, and so this basically means that it is being used currently until we unbind it. And maybe I should unbind it down here, I guess. Let's do that. I don't know, can anyone tell me in the comments, if I don't unbind it, does it create a memory leak? I'm not sure. But so this is the way you unbind, is you bind to 0. Okay, so we're using the program that we made. Then this is our loop, okay? It could be like a game loop. As long as the window should not close, then we do stuff. I'm clearing the color. That was what made the background color, so if you want to change the background color, you can play with that. I clear a color buffer bit. I forget why I do this. Maybe it's not necessary, but I'll leave it. And we draw a triangle. Well, there's 2 in this case, so that's why it's number 6. If it were 1 triangle, it would be number 3. It's per vertex. So 1 triangle, 3 vertices. If it's a rectangle, we draw it with 2 triangles, which is 6 vertices. And I believe this is the size per unit here. I believe. I kind of forget what the 0 part is there. Sorry, these videos are not perfect and all that. It's a lot of work. I mean, I got this set up. I had not done it on Windows before. I had done it on Mac, and recently I decided to add stuff to do it on Linux, and I thought, well, if I'm doing it on Linux, I might as well make videos. And then when I started making videos, well, most people are using Windows, so yeah, it's just a lot of work getting all of the different platforms, testing them and everything. And if you want to help support the channel, do check out my Patreon. Sharing, liking, subscribing, and commenting all also help. So, okay, so then we swap the buffers. So at some point I'll be making videos about frame buffers, but just kind of be aware that there's basically 2 frame buffers. I don't want to get crazy into the explanation of it, but a frame buffer, just imagine it as a set of data that represents a screen or a window. So it's a rectangular set of pixels basically. And that frame buffer, we have 2 of them at a time, so that we have one that we're rendering to. Once the rendering is complete, OpenGL swaps it to the frame buffer that is being rendered. If you didn't do that, if you swapped it before the rendering were complete, then you would sometimes have frames being rendered that are incomplete, and so it would look buggy and you would have artifacts and it would be bad. So we wait until rendering is complete and then we swap the buffers. And then we do glfw poll events is getting input like keyboard and mouse, but we're not using it yet, but I just have that there anyway. Also, I need to learn a little more about vsync. I know that vsync is something on macOS and Linux. I'm not sure if it's called the same thing on Windows, but we don't need this rendering like an insane number of frames per second, like 250 or something. But we're going to get into that later, and I'm going to think about that stuff later. It also has to do with getting the program to not run constantly. That uses 100% of the CPU. If anyone has a link to GitHub or something that has a good solution for that already, let me know. I think I've done this stuff before, but I'm just having to redo it. And here we have unbinding that I just wrote and return 0. Okay, so that's it. I will go over these 2 functions next. Yeah, so let's go into that if you're interested. If you don't really care, then go ahead and check out the next video. Alright, so setting up the vertex array. This is where I pass in the actual vertices, and we have a top right. Yeah, you have the position written here in comments just for convenience. Of course, this would be different if you're working with something like a cube or some other shape. If you're working with models that you're importing from some program like Blender or ZBrush or something, then that's a whole different thing. We have to load a model, and we would probably use a library for that. So that's another video sometime in the future. We use this way of rendering. Now, there's a simpler way, but this is, I guess, the most efficient. I'm not sure, but this is the way that a lot of tutorials explain to do it. And so indices, it's basically saying which one is the first triangle, which one is the second triangle, because we're rendering more than one triangle at a time. We render 2 triangles here, right? So we're kind of just telling it which is the first and which is the second. If you play around with this, you'll get some funny looking bugs, and that's it, because it needs to be able to make sense of this data. Alright, and then, so this is a vertex buffer object, and an EBO is a element buffer object. They're just the little containers that are going to contain this data that we're going to pass into OpenGL in a second. So this is a common pattern in OpenGL. You generate something, so we generate vertex arrays. We do that once. We generate some buffers, the VBO and the EVO, right? Because these are just ints here. That int is acting like a handle. And so OpenGL will generate these buffers. It'll generate enough memory to hold. Well, actually, we do that later. We tell it how much memory to hold. Then we're binding this thing that we just created. So we could do this in like a different order and keep the VAO stuff independent, but this is just the way I did it. And we bind a buffer. So we bind a buffer, we buffer data. That's going to be the vertices. Here's the size of it. GL, there's another way to do this, is GL dynamic draw, is if you're going to be changing it a lot. It's just a hint to OpenGL that can improve efficiency. But in our case, it's static. We're just having it be a rectangle that just sits there. And EVO, well, actually this data is static. We're not changing it. Passing in, or rather binding the EVO and then passing in the data. In this case, it's indices, and we pass in the size. And also here we have the GL static draw. Now, the vertex attrib pointer. So I'll briefly explain about this. There's like, instead of explaining exactly what it is, I'll just give you an example. Let's say we had a texture that we are using to make the rectangle look like an image or something. You know, you can use an image that you have on your computer and use that as a texture. We would have another GL vertex attrib pointer, and we would actually, in that case, for textures, you have another set of vertices. You might think that, the way it works, okay, usually you have like a sprite sheet if you're doing a 2D game or something like that, and so you say where on the sprite sheet you want to render from. And so we use a different coordinate system for that, because that's the coordinate system within the sprite sheet, right? So we call those UV coordinates normally. And so if you were doing that, you would have another attrib pointer. We only have one. All we're doing this for is for it actually, so this actually gets used in the vertex shader. And I believe this 0 right here, whoa, stop doing that, Sublime. This 0 right here is the 0 right here, location equals 0. I think so. Don't quote me on it because I kind of forget a little bit, but I believe that's it. And the 3 is the size per object, basically. It's 3 of these little sets of data. So it's 3 bytes. Okay. And so 3 times size of float, yeah. Well, okay, if a float is more than a byte, then it would be more, I guess. And then I forget the last little parameter here. You can look up documentation. If you, you'll find some stuff. If you search OpenGL documentation and then type in this, it should come up. But yeah, that's the idea. So GL, and then we enable it. Or sorry, this is unbinding it rather. But it's let's see. Yeah, but this is enough to communicate to OpenGL. And bind buffer, we just unbind. This is from the last time we bound buffer data, or rather bound a buffer, which was here. So notice that in between here we didn't have to unbind. We could have put that in here, but I didn't bother. Now we unbind. I believe it's just freeing up memory there. And let's see, that's about it, and we unbind the vertex array object. So we bound the VAO, the vertex array object. We bound that here. We did a bunch of work while it was there, and then we unbound it. So it's that information is sort of connected with this. Okay, then the build shaders function. So it takes this int, which is like a handle, and I print out that we're building it. So we're going to have some error messages in case, because sometimes we make a mistake when we're writing the code for shaders, and it's nice to know that it was something wrong with the shader specifically. That is very useful information for debugging. So anyway, so during the compilation step, or while it's compiling, you'll see this pop out that it's building the shaders. And okay, so vertex, so again, this is a handle. It creates a shader. This is some kind of built-in thing. And GL shader source, this is what I defined in the beginning. with the source code for, okay. So yeah, we're passing that in, Vertex shader, and we're using this. So this is just communicating that this is the shader source code that we're gonna, or rather this is the handle and this is the code. And then we compile it and we then have this error message and we check if success. So it's kind of just stuff that you copy and paste in basically. We did all the same stuff for the fragment shader. It's no different. We already had these two variables here, so we didn't need to remake them. We just reuse them. And then there's a linking step, and we link, let's see, the shader to build, that was the parameter to the function. And so it gets, now we're working with that, and we attach it, the vertex shader and the fragment shader, link the program, GL get program IV. Okay, this is just a function for getting the like status of if something worked or not. And yeah, so it's about putting out an error message if it didn't link and compile properly. Well, actually just links. I mean, these are like object code that get compiled separately and then linked together. And then it's done. And we can delete the individual shaders because we have the full shader program. After that, we have shader to build. And so you'll notice that it doesn't return anything. It just did all of this for this particular int, this particular handle. It's kind of interesting way of doing things, but that's what it does. And that is it. So this was long, a lot of work just to make a rectangle, but it's all going to be worth it. And yeah, so this should work on all three platforms, and you got the different run scripts you can check out. Just run them with main.c as the argument. It should work. If anything doesn't work, leave a comment, let me know. And I should have said in the beginning, but it's on GitHub, and in the description I'll put the GitHub link. Okay, so you can download the code. That's about it. Thank you for watching. It is great, people who want to help out the channel, if you want to check out the Patreon and all that. Thanks for watching, and see ya. Bye.